And I have completed the project of EV with the ADAS system. So this is the title of the project, and we have used the STM32 Blue Pill and using the software STM Cube ID and Pixim lab, and then at last we will get the output in Python dashboard. So the internship overview is I got the hands-on experiment on a embedded system internship on the STM32 F103C8T6 Blue Bill using STM32 Cube IDE and about the Hall library. So the internship over goal is to build a simulated electric vehicle with full ADAS. ADAS expansion is advanced driver assistance system, safety layer entirely in firmware. 5 cooperating modules were used for this project. One is the EV control, ultrasonic sensing, ADAS, fault detection, and UART command shell. All sharing common types are true common dot h. We used it this one. And this project is validated using Pixim Lab, which is an hardware simulation, and the Python dashboard where we will be fed live over the serial, where will we get the output. No physical hardware is required. And about the pin mapping, so we are here. I have mentioned the pin numbers which we used, which is called as GPIO and ADC. For the analog inputs ADC, PIO is used as oscillator pedal, and its efficiency is given here. I mean range is given here. And PA1 is used as the brake pedal. PA2 is used as the SOC seed. PA3 is used as the motor temperature. So the conversion formula is pedal percentage is equals to raw by 4095 into 100 and temperature will be raw by 4095 into 120. Here the raw is the data, live data. And PA2 is deliberately not reread every cycle. SOC after boot is tracked purely by energy integration. Digital input output GPIO B or C I have used a GPIO B, okay. And PB0 is used for the front sensor trigger or echo. PB2 is used for the left sensor trigger or echo. PB4 and 5 is used for the right sensor trigger or echo. And PB8 is used for the LED collision warning. PB9 10 is used for LED blind spot L by R. PB11 is used for LED fault detective. And about the real-time scheduling, that is about the time-based real-time scheduling. 2 interrupts-driven loops plus 1 free running clocks are used. So like here we have used 2 interrupts and 1 free running clock. So we have used 3 timings. Time 1 which is of 10 millisecond tick. Time 2 which is of free running. Time 3 which is of 100 millisecond running tick. Time 1 is generally used for EV control loop. Time 2 is used for microsecond clock. Time 3 is used for sensor and ADAS loop. So the files are the interrupt will be coming for every 10 seconds, calling the EV update function at 100 Hz, the fast physics loop for torque, speed, power, and SOC. Interrupt fires every 100 milliseconds, which is called HCSR04, read all function, ADAS update function, fault check function, and cell process function in sequence. No interrupt for time to no interrupt. Just the continuously counting 1 megahertz timer, pooling directly to the time ultrasonic echo pulses and blocking delays. So these are about the time-based scheduling. And next we go to the EV controller. This part is about entirely about the EV controller, how it is designed and everything. So EV controller is made of state machine and torque. So the operation is parked, ready, driving, regeneration with the fault override. So vehicle state machine. Now we can talk about the vehicle state machine. Parked means torque is held at 0. So it moves to the read one when it moves to the read once the pedal is pressed past 20%, 2%. So when torque is at 0 and it moves to the ready, only when the acceleration pedal is pressed and ready transitions immediately into driving. A button or a key interlock can be added later. So ready transition will be immediately happening to driving. After we press the pedal, driving will occur, right? So that's what they mention here. And driving will be transferred to driving and regeneration can be both done 2 and 4. So this one toggles based on whether the brake is applied above the regeneration threshold, that is 5 percentage. So when you are driving, if you apply the brake pedal, the regeneration threshold will be occurring, which is of 5 percentage, and after regeneration, it will enter in the regeneration and thereby it stops the vehicle. Fault freezes motor torque completely and skips all physics until cleared. Torque and regeneration braking. Drive torque, the formula is acceleration percentage by 100 into 150 nanometer into mode cycle. Mode scale. Mode scale is given by ECO zero point 0 into normal 1.0 into sport 1.3 into 130 percentage booster. Above the regeneration threshold, brake percentage maps to a 0 to 70 percentage regeneration level, which produces negative torque up to 80 nanometer. And when we come to the ADAS part, there are two conditions, collision warning and TT&C or TTC. Its operation is turning ultrasonic distance along with speed into a graded alarm. TTC is nothing but time to collision, and its formula is front distance, which is m, divided by speed, which is denoted in meter per second, and it is computed while moving greater than 0.5 millisecond. That is speed when the speed is greater than 0.5 millisecond, and with it should be within 200 centimeter, and the distance should be here they gave in meter, but it's in 200 centimeter. And otherwise, TTC is usually held at 99.9 seconds, which is a safe value. And it is also clamped to a 0 to 99.9 second range for a clean display on the dashboard. And coming to the collision warning, that is the graded collision warning. It is critical if front is less than 20 centimeter or the time to collision is less than 1.5 second, and it gives warning if front is less than 50 centimeter or time to collision is less than 3 second. Hysteresis counter 3 cycles holds each alarm active briefly after the condition clears, preventing rapid flicker between states. And there is a separate counters for warning and critical. So a critical event correctly resets the warning counter. Next is about the ADAS safety, blind spot, overspeed and fault safety. These are the constraints which we are to consider while talking about the ADAS safety. The remaining ADAS checks how faults override the vehicle. So blind spot and overspeed. Blind spot is nothing but it occurs when side distance is less than 30 centimeter and speed is greater than 20 kilometer per hour. So it never comes while stationary or parking when a brake is applied, in short. Overspeed advisory fires above 120 kilometer per hour. Overall alarm priority is like critical, which should be greater than the warning and should be greater than the advisory, and it should be greater than the none. So PB, as you can see here, PB 8, 9, 10 LEDs are driven directly from the collision or blind spot left or blind spot right flags. Fault detection. Three fault sources are used. Motor over temperature which is greater than or equal to 90 degrees Celsius. Critical low SOC which is less than or equal to 2% and a critical collision that has a valid sensor data. Faults are bit mask. Fault OD, these two functions are used, these three functions. So multiple faults can be active at once. Any active fault forces the vehicle into the state fault, freezing torque immediately, not just the something like logged warning. Auto clears back to driving once conditions are recovered. A manual fault clear resets the vehicle fully to a space parked state. Hmm. Going to talk about the command interface. For this, you'll be using the UART command shell, which is a live command interface for demoing every subsystem. So UART basically consists of transmit and received terminals, where transmit in STM32, transmit is P809 and receive is P810. So here in this project, UART is basically used because bytes arrive via the UART received interrupt to the ring buffer, and we have used a cell process function which parses the complete lines into the main loop, and the receiver terminal is never blocking. So that's one point. And second point is that it supports black space editing and also the character echo, so it behaves like a real terminal over the terata. And when we these are the uh, commands or commands which we be using mode, echo, normal or sport. These are used for the switch drive mode. Speed reset, which is in kilometer per hour, is used to inject a test speed. SOC state. SOC stands for state of charge. This is just represented in PCT. It is used to inject the battery. SOC means battery. An obstacle, which is in centimeter, it is used to simulate the front obstacle. Fault inject motor or SOC or COL, it forces a false condition. Status help reset full status thumb. Like status is used for full status thumb and help for any help functions. Reset is just for rebooting the system. This is all about the UART command cells where like what are the commands are used. And next is the telemetry and visualization, which is nothing but the status telemetry and Python dashboard. Status telemetry is nothing but the UART telemetry. So it is the bridging firmware state to a live visual dashboard. Here we will be connecting the firmware state like status and to the visual board. UART telemetry, UART 1 is used at 115200 baud rate, and interrupt is driven on both the transmitter side and as well as in receiver side. So the print status function, which will send a full human readable snapshot, and this function includes speed, SOC state of charge, torque, temperature, range, drive mode, pedals, ADAS distances, TTC, and alarm level and active fault flags. The compact main loop status line
runs once per second alongside the interactive cell. So these are about your telemetry. And coming to the Python dashboard. So we have used VSPE, which creates a virtual serial port pad that lets the MCU UART stream to reach the Python application in real time. So, and the Python dashboard will visualize speed, battery percentage, motor metrics, and the bird eye ADAS view with live left, front, right distance. We will be seeing this left, front, right in that demo video. Up next demo. And the Terraterm will be running in parallel as a raw terminal for issuing cell commands during development and demos. Cell commands, so as you can see this one. So yeah, this is all about the project. And now we can see the demo.
Now let us see the demo of the project. So I have opened the project now, and I am going to enter the value as you can see here. We are getting the values. And when I decrease or increase the front level, we will get the values according to that. So this is the as you can this is the front, left, and right. Now we are going to the VSFE to view the Python dashboard. Let me set the values. And I'm opening the Terraterm. And after setting the values, like entering some commands, so if I adjust the value, like I'm adjusting the front level to the maximum, and sorry, lower and left to the maximum and right to the same level as the left, and adjusting these icons. So on changing the left, right, and front, depending on that, the values output will be changed. As you can see here. To be exited and run. And I'm opening my command prompt. And now I am in the attempt of opening the Python dashboard, the Python code. This is the UR and the ADC. So this is the Python dashboard code. As you can see, it is open in the VS Code. Yeah, so if I give enter, I'm getting the Python dashboard. So this is the Python dashboard where we can see the output, entire output in a better way. As you can see here, battery is in full charge first. And
So this is the overall project demo. So thank you.
वीडियोस बनाने हैं फिल्मोरा है ना।